Problem number 19. A small rock is tied to a massless string of length 5 meters. The density of the rock is twice the density of the water. The rock is lowered into the water, while the other end of the string is attached to a pivot. Neglect any resistive forces from the water. The rock oscillates like a pendulum with the angular frequency of which of the following? Solution for problem 19. The submerged rock experienced an upward buoyant force equal to half its weight, since it displays a volume of water that weighs half as much as the rock itself. Thus, if the rock were free-falling in water, it would accelerate downward with an acceleration half of free-fall acceleration. G effective equal G over 2. The angular frequency of a normal pendulum is given by formula square root from G effective over L, which is after putting numbers we have 1 radians per second. This is the answer A, and this is the solution for problem number 19. Problem number 20. A uniform rod of mass big M and length big L is hinged on a horizontal surface at the bottom. Its top end is connected to two springs, both with a spring constant K. What relation must M, K and L satisfy such that the position shown in the figure is a stable equilibrium? Solution for problem number 20. For stable equilibrium we have a condition that if we have a small displacement from this equilibrium, the potential energy must increase. So it means that when we compress springs, the increase of potential energy will be 2 times 1/2 K L theta, where theta is a small angle displacement, squared minus change of potential energy for center of mass, which is 1/2 mgl multiplied by 1 minus cosine theta. And this must be greater than 0. For small angles, we have 1 minus cosine theta approximately equal 1/2 theta square. When we put this in this inequality, we have this inequality. So it means that if we take theta square out, we have this condition 4KL must be greater than mg, which is answer A, and that's the solution for problem number 20. Problem number 21. A spherical cloud of dust has a uniform mass density ρ and radius big R. Satellite A of a neglectable mass is orbiting the cloud at its edge in a circular orbit of a radius big R, and satellite B is orbiting the cloud just inside the cloud in a circular orbit radius small r, where r less than big R. If Vi is the speed of satellite I and the Ti is the period of satellite I, which of the following is true? Neglect any drag forces from the dust. Solution for problem number 21. If we have a satellite which is rotating around spherical cloud of radius r, the centripetal force must be equal to force of gravity from dust inside of this sphere, and the outside cloud is not affecting this satellite. The force from outside part of cloud is 0. So it means that we have equation mv square over r equal gm big M over r square, where big M, that's the mass of part of cloud inside of a sphere radius small r. And we have mass of this part of the cloud is proportional to small r cube. So it means that we have this equation to find what is speed v. That will be this expression. It means that speed v is proportional to the radius of this satellite. It means that for satellite A, speed greater than for satellite B. And to find what is period, we have to divide total circumference of this orbit over speed. This period equal 2 pi small r over v. And using this expression, we see that the period does not depend from radius. So it means that both periods are equal to each other. It means that answer E is correct answer, and that was a solution for problem number 21.